Good afternoon. Guess we'll get started here. I'm Brent Bigonger, and I'm a database engineer at Amazon. I'm a longtime DBA who's very recently kind of jumped in the Postgres pool, both feet first, as we have migrated several hundred databases over to Aurora Postgres. So, going to talk about that our migration story and some of the lessons we've learned. In order to do that, the department I work for is Amazon Fulfillment Technology. You can kind of think of Prime, which is everything that happens in the fulfillment centers, all of the inventory movement in the fulfillment centers and all of the different teams that work in there. And so I'll tell you a little bit about that, as well as some technical challenges that we had to overcome along the way, and really just our migration story. So AFT, Amazon Fulfillment Technologies, this is a picture of one of the fulfillment centers. We migrated approximately 350 of them worldwide. So each one of them had a source Oracle database that represents one fulfillment center. And you can see some of them are very large. They range in size from tens of thousands of feet to over 1 million feet. And they have hundreds or even thousands of FC associates and miles of different conveyances pushing totes all along. So there's, to give you an example, one of our larger ones in size at least is about 1.2 million square feet. It's about 6 of the largest Costco's or 28 football fields. So there's a lot happening there, and about 2,500 employees or so. And a lot of systems in place to do inventory movement and packages. One of the interesting parts of this system is that we deal with physical machines and processes and people. Some of these automated, some of these synchronous, some of them asynchronous. But everything really requires the inventory picture, to be able to see where an item is in different stations. So, for instance, these are showing inventory bins. Most likely, this associate is picking items. He's looking at a handheld scanner, getting the items that need to be picked, putting them in a tote, and sending them along conveyance to the next station. Other FCs are automated, and where they'll literally pick up a shelf, and the FC associate is going to be stationary, and the robot will bring the shelf to him, and he's able to do his job. But one of the things that's important to us, and that I wanted to mention, is latency. Because he's looking at this in real time, and he has to pick things very quickly. The SQL queries and things like that from the database have a very strict SLA in order to allow him and 100 other associates doing the same job to not be standing around. Another station here is the pack station. They're taking the items that were in this tote, and software is telling them size of the box to use and other things to pack it with and to put it on the conveyor belt to be sent along. And one other picture I just wanted to show you is, again, why latency is important. You can see in the background here, that red light is a scanner. It's basically scanning a label that a pack associate has put on a box. And what it does with that is it looks up that piece of inventory or what's in that shipment, and it's going to make a lot of business decisions based on what's in there, based on the weight, based on how many items it is, based on where it's shipping to, based on if, for instance, nail polish is in there. You wouldn't think so, but it's a hazardous item, has to be treated a little differently. So in real time, it's making decisions, and it's ultimately going to print a label and slam it on the box. So all of this has to be done rather quickly, accessing database queries. So if there's any latency in these API calls, this automated conveyor belt, as it moves along, is going to kick out this box and cause problem-solve associates to have to deal with this manually, and so it's obviously not desirable. So as I mentioned, we did migrate about 350 of Oracle source databases. They all had the same schema. They were all set up as Oracle Data Guard with Active Data Guard. in our Oracle environment. And one of the tall orders to Aurora Postgres is to have to live up to supporting 20 years of DBAs kind of wrenching and tweaking and optimizing queries and migrate that over to Postgres and have that pretty much just work. We also had minimal downtime requirements. I'll talk a lot more about what those were as we go along, and dozens of different microservices. And there are a lot of, having 20 years of legacy systems, we didn't know every single use case that was there. We knew there were probably some that were missed, little jobs, little things, little systems that were in place and just running that teams may not have known about. And so there was a lot of dependency analysis that we needed to do. And we talked about the call latency as well. But all in all, these 350 databases, we empowered our service teams to do migrations kind of on their schedule. So what really ended up happening is we did well over 1,000 migrations because we did them at different times after we decoupled some of these relationships. But so that was just some of the migration complexity I wanted to mention. At a 50,000 foot view, this is kind of what our environment looks like. We have a number of different teams, such as receive or stow or pick and sort and pack and ship. All of these were accessing inventory calls to get the state of inventory as they perform their functions, as well as directly accessing the Oracle database as well. Some of the challenges in our legacy Oracle on-premise systems were definitely scalability. It was difficult to scale. In an Oracle Active Data Guard, you've got primary and a standby instance. And in order to scale up to the next instance size, we need to restore a database, bring it into our Data Guard replication, and then after that's in place, fail over to it, and then do the same thing on the new standby as well. So scaling up to another instance actually was a lot of effort and required custom hardware. We were on the largest hardware that was available to us at Amazon.com, not AWS, but this hardware had to be specially built for us to support our I/O requirements and such. Other challenges for us were availability, for instance. If we had a failover and had a hardware issue, that had to be worked on by data center technicians and involving our team to make sure that we can bring that back to a healthy state. So it sometimes took many hours to get back to a high availability of active replication, and as well as failovers took a little bit longer, 1 to 2 minutes, 3 minutes approximately. And the hardware management was more difficult for us, having to forecast and look against our forecast to ensure that our peak season, we're going to have to juggle around hardware at times if forecasts are off for our different database systems or different FCs, and created a lot of operational burden. So one of the things we did, our service teams kind of took a step back and looked at their services and really looked at what was the optimal persistence layer for their services. So looking at these purpose-built databases, relational has obviously been there for many, many years, but in a lot of cases, the service teams were able to determine that that's not optimal for them. They actually could be better suited in a key value store such as Dynamo or any other number of kind of purpose-built databases that better suit their service. So what we ended up with was something closer to this, which is we have a set of purpose-built databases that each team evaluated, and they can access what technology makes sense to them. Now, they still all need to access the inventory picture, and this is a foundational service, so teams worked hard to ensure that any inventory calls were done at a service layer instead of going directly to the database, which has just kind of been done over 20 years of legacy operation. But when calling inventory, those databases and several others here, they access Aurora Postgres, but the other services can make decisions what's the best technology for them. So I won't spend too much time on this slide. We've kind of talked about why we chose Aurora Postgres, performance and availability that suited our needs, as well as Postgres's feature and SQL parity with Oracle was important to us. Scalability, the ability to scale vertically or horizontally, and we'll talk more about some of the decisions we looked at for horizontal scaling as well. And that it was a managed service, and we have taken we've taken advantage of the fact that we now have snapshot backups and to use those in non-prod environments and things like that. So to talk about our migration a little bit, the preparation, a couple of the kind of overall design patterns that we looked at were just to separate our AWS accounts into prod and non-prod as a kind of a best practice, as well as look at our applications and what could we leverage to use a fleet of readers to be able to have the ability to scale horizontally. So application teams looked at their code, and we are able to make use of up to 15 readers at this point for our read workload that's applicable. And then the utilizing snapshots and clones, as I mentioned, as we're able to obtain a data set for a large database and then slowly build our test harness around that, getting better in our load testing, and to be able to use that, we had set out to make sure that we can do this with our largest database volume. Of course, security at different levels, encryption in transit and at rest, something that's very easy to do as we move into Aurora Postgres. And we plan to automate using standard AWS APIs and CLIs, which was critical to us as we're migrating, doing over 1,000 migrations. One of the other things that we plan to do is not just do one or two kind of test cutovers, but a half a dozen or more. And we really learn things every time. So this was something that we probably could have gotten by with a couple of them, but doing multiple cutovers really allowed us to learn every time and get better as our automation kind of continued. So I'm going to go through some of the differences that, going from an Oracle database, these are kind of the bigger ones. There's certainly a lot of considerations to make, but for us, timestamps, we had to really consider that when we have an application server fleet that has a shared connection pool that's connecting to n number of databases in a region, like 100 databases. Our applications actually expect the server's time zone, which is what Oracle's sysdate provides, versus like a clock timestamp giving a client time zone. And I mean, if you were going to build an application today, you probably would use UTC and not have some of these maybe issues, but this was legacy, and it's just something that we had to consider, the time zone differences in our applications. Partitioning differences were also something to consider. For instance, we use partition tables to manage our data lifecycle and to just age off old data, date range partitions. And we had to at least start conversations around not being able to have global uniqueness across an entire table to be able to ensure that applications aren't relying on that. And if so, find some ways to code around that. Because even with improvements, from 9.6 to 11, and there obviously have been a whole lot, there's still feature differences between what Oracle provides and Postgres. Another consideration was the collation of character types. So for instance, text, varchar, and char data. In Oracle, uses C collation, and when you spin up an Aurora Postgres database, by default you get English US. So to take a look at the character types here ordered by a value, in different ways, they're sorted, in this case, 3, 2, 1, whereas in Oracle, that same correlation difference would have been 1, 2, 3 in that way. So that can, if your applications depend on that sort order for various queries, that's also something to consider. And it was also something to consider for our migration. We used the AWS database migration tool. That also does validations based on collation order. As I mentioned, the analyzing dependencies was a big issue for us, or a big challenge, because we didn't know all of everything that accessed a bunch of shared tables or views. We had a lot of materialized views that were cross-database and accessing different databases and ETL jobs. So it was a big web of dependencies that we really had to unpack to start this, and spent a lot of time doing that. We started looking at Oracle views, DBA hist, active session history, as well as periodic sampling of $SQL or $SQL area to capture the different SQLs, as well as logon triggers, and very specific logon triggers in some cases. But to be able to capture this data and provide it to our service teams in order for them to programmatically go through this and identify those dependencies. And for instance, things that are running on a standby as well. Those we have a lot of data warehouse jobs, or we did, that were running on an active data guard standby. All of those kind of needed to be considered in unpacking this dependency web of 20 years of development. Of course, there are other ways many ways to look at and try to understand what's querying your database. There's auditing and things like that. That was kind of a heavier approach, and we were able to do it without doing active like Oracle auditing, which is more with a more greater performance impact. So in our migration, I'm going to talk a bit about our automation at least a high level. And so launching databases and integrating with a lot of different components there. We first started with being able to obviously track these databases, hundreds of databases, and entering it in a management schema of ours, and then creating reserved instances. For instance, it might seem a little strange that we pay AWS, but Amazon.com as a customer might be shifting from one hand to another at some level, but our department is charged and in the same way as an external customer, and our budgets are based on that. So we're very frugal to look at reserved instances to cut down on demand pricing. So creating reserved instances and then creating databases. We onboarded various different ETL jobs, as well as created schedules jobs for things like our partitioning, like I mentioned, rolling off old data, integrating with CloudWatch, creating monitoring on top of that and alerting, and then finally applying the DDL to our Aurora Postgres databases, and finally kicking off DMS was our tool to migrate the data. We had a number of migration requirements to do this. One was kind of to do no harm, of course, in our live production systems that would impact FC associates, and a relatively short downtime window, from about an hour to 2 hours at the very most. And the Aurora Postgres performance obviously had to be on par or better than what we were moving from. And so when migrating data, we needed to perform full load and keep in continuous replication and have that validation done as it's streaming by. Setting up migration a week ahead of time and being able to validate that data. We didn't want to find out on our migration day that once we cut the stream of replication that we had a data error. All of our schemas, all of the schema is the same, but obviously data in different regions can be different. Do you have a question?
Yeah. So how about this streaming done? How is the replication done?
Sure. I'll show you in one more slide. I'll give a big picture. But the database migration service is what we did use, and it was using change data capture to do the streaming, so ongoing replication, and then to have alarming and monitoring as well on that. Automation, of course, was key to our migration efforts, to have the automated provisioning and data migration, as well as the ability to, if we're going to do 1,000 migrations as planned, we're going to have to be doing a lot of these per day. And so in our kind of peak migration time period, we often did about 20 of these plus a day. And so here's a very high-level picture of what it looked like for us. For using the AWS schema conversion tool to access our Oracle source database, obtain the DDL and the schema, convert that to Postgres DDL, and then apply that to an Aurora Postgres instance. And then once we applied that, of course, then starting the database migration service to access our source database, perform a full data load, and then start that CDC ongoing replication. So I want to talk about, a couple of things that we did in the migration as well, is that we never planned for a zero downtime migration. It's probably we could have. Technically, it would have been possible or very close to zero, but it wasn't a requirement, and it really saved us a lot of effort to plan to have small downtime windows as opposed to very complicated processes that would have had to support that. So our migration methodology to do that was helpful. This was primarily a lift and shift. We didn't make too many code changes unless we needed to, or we picked up a piece of software where it just made sense to make changes. We started, of course, with a lot of manual migrations and a handful of pilot databases. Added automation, and then we migrated our largest database. And that was done intentionally to basically exercise that we could do it for all of the rest of our very large databases as well. And then as we went, we added full migration automation. So I wanted to kind of talk about the migration automation that we built. All of this is a little bit complicated diagram, so I'll walk through pieces of it. But it's based on Amazon simple workflow, and it's intended for a DevOps operator to kick off via a CLI or a web UI in different pieces, and have this system description tell basically. The system description is going to describe every step along the way, and it uses a requires or provides and invokes type of step through. So if you're going steps 1 to 100, we step through serially for 1 through 5, and then step 6 invokes 3 different parallel paths, and then on step 7, all of those have to complete, and it going through this workflow engine. So simple workflow is able to kick off these different components here. For instance, a SQL component, we needed to make changes to source or target databases throughout the migration. So to ensure that that we don't have any more data in our source database, we can have our application teams turn off their applications, but to be additionally sure, for instance, renaming tables, we needed automation to go and execute a SQL script. So this automation, the SQL component, is going to execute various different, this SQL script and a dozen other ones. So these components are kind of the, the what to do, and the SQL script is how to do it, as well as the Java components as how our service teams integrated with this and interacted with their services or DMS components. DMS component was able to interface with the database migration service and so forth. So like I said, what we ended up with is essentially being able to have a DevOps operator start multiple workflows and do this. And while like database teams and software teams were available and on call as our migrations got started, it was really automated, and DevOps was able to perform all of these migrations 20 plus a day as we went along. So after performing migrations, want to share some of the lessons that we learned along the way. Having schemas that were quite old, not all of our tables had primary unique keys. Probably 98% of them did, but not all of them. And we tried for a while to kind of, using the database migration service, try to work around that in different ways. And it was really just fighting an uphill battle. So we ended up going and doing kind of the right thing and adding PKs, UKs to the tables that didn't have it. It's certainly required for lobs and as well as for data validation. So, doing this again, looking at some of the deficiencies that we ran into with DMS were really just kind of our poor schema design over the years. Identifying lob tables, and DMS in particular treats lobs differently in limited lob mode versus full lob mode, and now inline lob mode is in limited lob mode you can tell the database or the DMS agent how large that lob is going to be, and it can effectively do this much faster than in full lob mode. It has no idea how big this lob is, so it has to transfer them one by one. Inline lob mode is a blend of both of those and was recently released by the DMS team. One thing that we found very quickly was using large replication instances really helped us out quite a bit in the replication. So like an R4 instance class series, and it really was minimally, it was very minimal cost. Yeah, please. That's right. Yes. Yes. So yes, I'm sorry. So she's asking about when I had previously mentioned that global uniqueness on a partition table wasn't possible in Postgres, and now I'm showing here, probably kind of confusingly, that a primary key is required for some source tables here. In the source database, we did have global uniqueness for our source tables. Oracle does provide that. In Postgres, still have primary keys and unique keys, but they are at a local partition level. So if you're relying on the database to ensure uniqueness globally, if you're making an insert at 11:59 p.m. and then you have a daily range-based partition, in Oracle, if you inserted it at 12:01, that's still a violation. If you have a global view of your entire table, as in Postgres, that would just be double inserted. I'm sorry, go ahead.
In other words, DMS requires a PK, but it can be on partition level, not on global partition.
Yeah, that's correct. In the source database, you require a primary key, but it doesn't have to be global. It could be local as well.
Just to add one quick comment on that. The primary key requirement for a source table is for the
You can do it without it on the source as well, but one of the pieces that you miss out on is data validation. And for lobs, you certainly can't. You do need a primary key or a unique key. So monitoring our replication instances. DMS does make it fairly easy to use CloudWatch metrics and alarms to ensure that the availability of the instance or that the replication lag and things like that. One of the things that we also did was use a heartbeat table, for instance, which is a very simple kind of per DMS task. So if you have a source database and have a source table, you're basically inserting kind of a dummy record with a timestamp, which gets then replicated over to the target side. And one thing that gives you is to pretty easily check how latent that DMS task is. But also, when you're doing your cutover, you can basically ensure that once you've stopped writes on your source side, that now that timestamp that you've stopped the writes and you have this heartbeat happening, as long as the heartbeat timestamp is greater than when you've stopped your writes on your source, you know that you have every piece of data replicated over. It's just kind of a quick and dirty way to also validate that. Our applications have historically used a number of triggers to populate created by or last updated, in some cases, columns. And to do that, you just need to be ensure that you are enabling those after your Postgres replication is stopped. Otherwise, you won't be able to validate the data properly. Other migration lessons learned. We took a look at our data lifecycle retention. And as I mentioned, in partition tables, in one case, we having these conversations of if we had 6 months of data retention, do we really need that? And it provided a lot of benefits because sometimes people forget why you need 6 months of data, and reevaluating that in a lot of cases we found that we really only needed 1 month of data. So for the migration, it's much easier to migrate a month worth of data than 6. But also on the, once we migrate to Aurora Postgres, now you're paying for storage costs. So if you migrate the data, you really have no way once you drop the data and drop it down to 1 month, you also don't have a very good way to reduce that retention and actually reclaim the space in the Postgres database. So reducing the retention and having those conversations prior to migration was critical to keeping our database very small and lean, what we did migrate. We also kind of took the opportunity to add instrumentation of our SQL statements. So for instance, adding comments as to which APIs these calls are coming from. And that's been very helpful for troubleshooting. We don't have to spend a lot of time trying to figure out with our application service owners which API is making these SQL calls. And so that's been extremely helpful, especially as we're moving to a new database engine and we're talking with our service teams quite a bit. So having that instrumentation and having that telemetry into the origin of the SQL was very helpful. And it's allowed us to go into code repositories and really identify where that call is coming from and have a better conversation with our software developers. Sequences in Oracle and Postgres are not the same. Well, Oracle uses a global sequence cache where at a session level, it occurs in Postgres. Some of our applications, it actually made a difference in, while they didn't need anything like a monotomically increasing sequence, but it did impact when we had various different sessions and there were very large gaps in the data, which again, probably you wouldn't design that way, but legacy applications, that was the issue. We did a lot of testing and just setting the cache value to 1, so essentially no caching. We actually didn't see any any performance impact from that. These are very OLTP-like applications, and so batch workloads, your mileage probably will vary. The use of verify full for SSL, and null again is treated differently. An empty string and null are treated the same in Oracle, whereas in Postgres, it's, an empty string is truly stored as an empty string. So if you have, applications that matters, that's something to consider. Did you have a question? No, sorry. As I mentioned, our applications had a number of triggers, and so having exception blocks in our triggers was consuming transaction IDs that we found pretty quickly. And even when the exception was not raised. So burning through transaction IDs obviously isn't something that we wanted to do. And the fix is pretty easy to just change the exception block to raise a notice or an error. But certainly it's something to take a look at, especially if you have triggers that are called. So in difference in engines, Oracle, if you have a uncommitted transaction, we had different sniper jobs that may look at if there are sessions waiting and kill those for various reasons, how long they've been waiting or how many sessions it may be blocking. But if in Oracle you have an uncommitted transaction and nobody's really waiting for it, it's also really not that much of a problem in Oracle, but in Postgres, obviously it can block dead tuple cleanup and multi-transaction cleanup. So would strongly consider looking at the idle in transaction session timeout and having some conversations with application teams. We honestly didn't realize very much that some applications just kind of left transactions open for various reasons for a very long time that was truly unnecessary until we started seeing this and moving over to Postgres where it does matter quite a bit more. And then not having global temporary tables was not a showstopper, but in some cases, instead of having a local temporary table, we opted to make SQL changes to not have a lot of create and drops happening all the time with a per session level. Obviously, auto vacuum is a huge topic, and I think a colleague of mine has a very good session on that later. But one of the things to certainly look for and alarm for is unvacuumed transaction IDs, and CloudWatch has a metric and set alarms on that. So at a minimum, really should be watching that along with a lot of other CloudWatch monitoring. Lots of ways to monitor for your unvacuumed transaction IDs, pgstat all tables, and looking at live and dead tuples and the last auto vacuum date. And then just to kind of throw out that the auto vacuum settings really are just defaults and can accommodate all of our situations. So taking a look at each per table is very helpful, and looking at your type of table, maybe the fill factor, filling a page all the way to 100% might work really well for an insert only table, but you probably really want to reconsider changing that if you have a very heavy DML table that does a lot of updates, deletes. And then once moving on to Aurora Postgres, Performance Insights is a very helpful tool to get an idea into the weight system. And another colleague has another topic on that. I've seen that he's delivered that. It's a very good talk that I believe it's on Thursday. 4:20 on Thursday. So Performance Insights really allows you to go and dive into the SQL level and to be able to dive deeper into and using weight events. Recently added, I'm really a fan of counter metrics as well. allowing you to get an idea of both in-database and OS metrics here, and allow you to take a look at what's been happening. But Performance Insights is sampling at a 1 second level, so you can get very, very granular as to what's happening at what time. And for instance, if you wanted to see transactions committed, or a dozen or two other metrics, it's very helpful. Utilizing CloudWatch dashboards and alarms, they just, you get these, they just come along with going into RDS or Aurora Postgres. Very helpful to just use them. And after we performed our migrations, we were very concerned about getting those migrations done, but afterwards, obviously, making sure that we were being frugal about things. So AWS Cost Explorer is very helpful to kind of slice and dice and filter down what you're paying for. You're paying for storage costs, you're paying for backup retention costs, you're paying for IOs in the database, all of the things that you do get charged for. So to kind of sum up a lot of the performance benefits that we were able to get were to be able to support our query latency and no backup penalty to take our backups, and scale to our workloads. Being able to scale up and down instance sizes is a big benefit that takes minutes now instead of many hours or even days, and to leverage horizontal scaling for our reads as well. The availability aspect of much faster failovers, when we see approximately 30 seconds for a failover, is very helpful, and maybe even more significant is being able to get back to a high availability state in minutes or even seconds. But even in the worst case of a hardware replacement, the AWS control plane will replace that instance in a matter of minutes to get us back to a fully high availability state. Being able to provision our hardware and not have to attend to working with data center technicians to try to get healthy hardware after a problem has happened, after a RAID controller failure, it's really helped with our operational burden. And being able to leverage all of the APIs and CLIs that AWS offers has really helped us to perform our migrations and then add to what we can do to manage a large enterprise fleet as we go forward. And there's no more Oracle licensing costs, which is nice. So thank you guys very much. Please let me know if you have any questions that I can help with. Yes?
How do you hold the stored procedures?
The question was, how do you migrate stored procedures? So also using the schema conversion tool, we didn't have a lot. It is much more complicated because it is complicated to turn that into PostgreSQL. A lot of the DDL that will be produced, even if it doesn't migrate, you will get some active hints to why this particular procedure didn't migrate over one-to-one, but definitely your mileage is going to vary there. Yes? Sure. So the question was, do we have any legacy systems using Oracle Streams? I know it does exist in other parts of Amazon. Not in our team. We didn't. So I can't tell you how they addressed that. But yeah, I'm sorry. So I think probably the man that you would like to talk to is right behind you there is Kevin. He knows exactly what you're talking about.
Well, Aurora Postgres will support on applications soon.
Yes, sir.
How big was your biggest database?
Size-wise, it was approximately, I can't remember, about 8 or 10 terabytes, 8 to 10. So not humongous, but sizable. There was a lot of cleanup that we were able to do that was very helpful. So the size of our Postgres databases is approximately 4 terabytes or so. There was a lot of cleanup that we were able to do. Yes. Mm-hmm. So on our migration, we haven't. Now it's become, now that we're in the AWS cloud, I think that it is a lot easier to kind of build systems in that way now. We didn't have any migrations that were needed for Kinesis or Redshift. Yes. So we do have data warehouse jobs, and they pull from a reader fleet, and we continued some of those, and we were able to a lot of our data was able to be integrated and pull from the service calls itself to be put in our data lake and and accessed via the in whatever way is necessary, not directly accessing the database. It's not preferred for us to have these ETL jobs, querying the live database, certainly.
You mentioned you were running custom hardware. I'm just wondering if you could give any kind of perspective of, what the hardware picture looked like then versus now.
Sure. The hardware picture was they were direct attached storage and with SSDs, and I want to say, I have to think back a little bit, 128 CPUs, 512 memory. So they were sizable systems. Right now, our largest instances are on R4 16x large, and a lot of those we've descaled quite a bit because after migrating, after we become a little more comfortable, that we just overscaled a little bit. So 16x large though. Yes.
So, how much time it took for your end-to-end process? Is it like estimate that your actual was like?
Are you talking about a total project, or are you talking about like per database migration? Sure. As we started gaining confidence, initially we had started data replication. Data replication is hard. So, making sure that we start the data replication long ahead. I need to wrap up here. Approximately 2 weeks, we would start data replication, get it in sync, and then just pick a date to cut it over. So, thank you guys very much. Appreciate it.